Okay, if I can have your attention please, we shall get started. Our speaker today comes to us from Italy, which places me in the position of perhaps having only the second best accent in the room today. After initially studying in Pisa and Trieste, he undertook his postdoctoral research at Caltech before assuming a professorship at UC Santa Cruz, where he is now the Director of Graduate Studies. When I saw the title of his talk, I was very pleased. It really ties in very well to a lot of the curriculum we have here at Sonoma State in astronomy, and is certainly a topic I know many people are very interested in, just simply for the sake of it being very interesting. So with that said, let's give a warm welcome to our speaker today.
Thank you very much, Tom, for the flattering introduction. So I'm really happy to be here today. I know I'll be a little less happy the next time I drive up here on the occasion of the May 12 Santa Rosa Ironman that I, for unknown reasons, signed up to. So today I will talk about the connection between the smallest and the largest things that we measure and that we think we understand in the universe. So scientists tend to be pretty arrogant about what they know about the physical world. I think there's very little reason to be arrogant. For example, we actually have no idea why the universe is filled up with stuff and not with a bunch of photons. And so another way to phrase this statement is that we don't know why the universe contains matter and essentially no antimatter. And yet another way to phrase this is what produced this asymmetry between matter and antimatter, when essentially all laws of physics are identical for matter and antimatter. We don't know. There's no fundamental physics that explains why the universe contains matter. Secondly, we know that the universe contains a lot of matter that fundamentally we don't understand the nature of. And what we call this matter is dark matter. And as I'm going to explain, the way in which we understand the formation of structures in the universe depends on the very existence of this dark matter. And we don't know what it is. We're certain that it's there. We're essentially certain in the sense of a scientific statement that it's there, but we don't know what it is. So let me start out by saying that cosmology is a composite word that comes from two Greek words, cosmos and logos. Logos, as you might know, means word, but it also means knowledge of. And cosmos means the cosmos, but it also, at its root, means the order. So cosmology really is the knowledge of the order that governs the universe. And that's something that, you know, as human beings, we've always felt the need to have. You know, we always felt the need to have some knowledge of what surrounds us. So in ancient times, Egyptians had this particular cosmological model. Later on, in Western civilizations, other cosmological models were developed because we really wanted to make sense of it all. Today we have yet another cosmological model called the Big Bang Theory. And this cosmological model is based sort of at late times on observations and direct measurements that we make of the universe. And in this other half, this is a log scale in time. It goes all the way back to 10 to the minus 44 seconds after the Big Bang. We make extrapolations. And this is the realm where folks like me, particle physicists, use particle physics to model and to understand what happened in the very, very early stages of the universe. Now, this is all stuff that we've learned by looking at the universe, literally looking at the universe, using photons, using light, at a bunch of different frequencies. For example, measurements of the cosmic microwave background, or radio measurements. We look at stars and galaxies with optical photons, with infrared and ultraviolet photons, gamma ray photons. But the new kid on the block is a completely new way to look at the universe that we just have put our hands on, which is gravity waves. Gravity waves that have been first directly, conclusively detected just in 2015, for which, of course, as you know, the Nobel Prize was awarded. This measurement is absolutely astonishing. It's absolutely mind-boggling if you think about it. So they're measuring how the very fabric of space-time changes by distances of 10 to the minus 19 meters. So 10 to the minus 19 is a billionth time smaller than an atom. Billionth time smaller than an atom. So you would say you're crazy, because quantum effects certainly do not allow you to measure things a billionth times smaller than the quantum scale. But in fact you can, using these very large interferometers and lasers, and very, very, very carefully controlling backgrounds of all sorts. I'm not going to get into this, but this is a magnificent enterprise that at the moment involves 2 observatories in the United States and 1 in Italy. And the type of observations that these observatories have delivered to us so far are things like mergers of black holes, tens of times larger than the sun, that have produced and delivered an incredible amount of energy that we got to detect. So the important thing for somebody who cares about understanding the universe that comes with gravity waves is the fact that gravity waves are intrinsically much better probes of the early universe than light. The reason is that light, it's very easy to block light. Okay, my hand blocks light. It has a harder time blocking higher frequencies, but ultimately, light of any frequency cannot penetrate the very early universe. It gets absorbed. Gravity waves don't get absorbed. So gravity waves give us a handle on essentially a whole new view of the universe across essentially all cosmic times. And we just now have opened our eyes to this new and entirely very, very promising way of looking into the universe. So let me go back to these and once again emphasize how we have now this completely new and orthogonal tool. So this model that I'm going to talk about today is called the standard cosmological model. And so why am I here talking about this model and not a model based on Egyptian goddesses? Well, the reason why I do that, and the reason that this is different from that, is that the standard cosmological model is, I'm going to make the claim, that it is a scientific theory. It's a scientific theory. So what do I mean by the statement that the standard cosmological model is, as opposed to other formulations of the cosmos, is a scientific theory? Well, I'm not a philosopher of science, but I know what some smart philosophers of science have had to say about scientific theories. And one important statement about scientific theories is that for a statement to be considered scientific, there's got to be ways to falsify it. So you got to make predictions that you can go out, make a measurement, and falsify. You can never verify a scientific theory, but for a theory to be scientific, you got to be able to come up with a prediction that then your observer friend can go out and test. So another important quote in the way I think about scientific theories comes from this Franciscan monk, William of Ockham, a long time ago said that entia non sunt multiplicanda praeter necessitatem. You should not multiply entities beyond necessity. A scientific theory is a theory that does away with any unnecessary ingredient, that it's bare-born construction that doesn't have any flourishing around it. And finally, my countryman Galileo explained, also a long time ago, that there is a very, very important feature to a scientific theory, which is the language it uses. The language of a scientific theory is lingua mathematica. It's mathematical language. Okay, that's a key feature of anything that we could call a scientific theory. And in these beautiful Italian words, Galileo, says that without speaking a mathematical language, we would just wander in this obscure labyrinth without any guidance. So mathematics is, one of the most important pillars in what a scientific theory is. So a scientific theory is something that makes quantitative predictions using the language of mathematics, that makes predictions that, in addition to being quantitative, so with a number attached to it, is also falsifiable. So it's got to be, at least in principle, an experiment that can test the predictions, the mathematical predictions of this theory. Also, a theory has to be consistent with pre-existing experimental results and at least as accurate as any theory that preceded it. Think, for example, of general relativity as the theory of gravity. Well, general relativity made sense at the beginning, even before making predictions that were compatible with it, because as a subset, as a limit of the theory, it contained Newtonian gravity. Okay, Newtonian gravity was a well-defined limit of a broader theory that included experimental evidences and experimental predictions of this pre-existing theory. And finally, and I think also importantly, it's parsimonious. So it doesn't have any unnecessary ingredient to it. It sticks to the bare minimum. So the scientific nature of the standard cosmological model has to do with the fact that, as I'm going to show you in one slide, this model makes quantitative predictions which are testable with observation, and it employs a bare bone minimum of ingredients. So what I'm going to talk about today, in the first part of my talk, is what the nature of these ingredients is. Okay, so what are these bare bone ingredients that we need? The predictions that the standard cosmological models makes are just amazing, are just incredible. So without essentially fixing any parameters, the standard cosmological model predicts the variations of temperature in the sky of the cosmic microwave background on angular scales that vary across 2 orders of magnitude. So from very, very small scales, very, very large scales. These are data points. You cannot even see the error bars of these data points here. And this is a prediction. It's not a postage. It's a prediction of this theory. Similarly, this is another prediction of the theory that tells you, as a function of the size of structures in the universe, going from very small to very large structures in this direction, it predicts how many, for example, galaxies of a given size, or clusters of galaxies, or dwarf galaxies, there are on average in the sky. And then you can count these galaxies and compare your predictions to your observations, and as a result. This is another sort of miracle of the standard cosmological model. This is the abundance of light elements. So heavier elements are synthesized in stars, in complicated processes that have little to do with the very early universe. But light elements like deuterium, helium-3, lithium-7, helium-4 are synthesized in the very early universe by a network of nuclear reactions that is very well known, that we know from direct nuclear physics experiments, that we can place in the context of a hot, dense, and expanding universe, and we can make predictions for the abundances of all of these light elements as a function of just one single parameter, which is the baryon density, or the number of leftover matter of the matter-antimatter asymmetry. Okay? As I explained in the beginning, we don't know what the value of this parameter is, but we can measure it. And then it's going to be the job of theorists to figure out why we are here. But the important point of this plot is that observations of the abundance of light elements all agree with one number, the baryon to photon ratio, or how many relic protons survive from the annihilation of protons and antiprotons in the early universe. And it's one number that explains all these abundances. Also, for example, the height of this peak with respect to this other peak is another indirect measurement of the same number, and they match. So the standard model of cosmology is a theory that makes a lot of independent predictions as a function of a certain number of parameters that once they're fixed, they're fixed. And any one measurement could falsify these predictions. You know, if, for example, you took this point here and you measure it here, you would kill the standard cosmological model. Okay? Or the height of this peak, which, by the way, right now is measured much better than what I showed in this video, is another sharp prediction. If the data doesn't agree with that, the model is excluded. So I want you guys to take seriously this model. It works beautifully. There's only one problem, and the problem is that the ingredients of this model are pretty weird. Okay, they're minimal, but they're pretty weird. The first ingredient that I'm going to tell you guys about is dark matter. So the picture we have of galaxies like the Milky Way is one where the visible stuff, gas and stars, is embedded in these huge, much larger halos of dark matter, very diluted type matter, much less dense than ordinary matter in the form that we experience. Even, you know, the gas in the air is a lot denser than dark matter in the galaxy at our position. We think that the same is true for essentially any galaxy, from very small galaxies to very large clusters of thousands of galaxies like the Milky Way. And we really need to have dark matter. So the way in which we think galaxies form has to do with the existence of tiny little density perturbations in the very early universe that grew under gravity. So the problem is that normal matter has, in addition to gravity, has other interactions. For example, anti-electromagnetic interaction. And so structures that would like to collapse under gravity cannot because of the pressure provided by electromagnetic interactions. So these primordial perturbations don't really affect normal matter up until very late times. In fact, the measurement of the size of those perturbations that we make with a cosmic microwave background tells you that if you only had ordinary matter, you could not form galaxies in time. It's a very simple argument that has to do with the linear growth of density perturbations. Without dark matter, galaxies would not form. There just wouldn't be enough time between cosmic microwave background decoupling and today. So that's a fact. So we do need dark matter because dark matter, being dark, doesn't have this outwards pressure. And so structures, clumps of dark matter, are free to collapse under gravity with nothing else pushing stuff out. Does that make sense, guys? So dark matter is a fundamental pillar of how we think structures form in the early universe. Okay? Without it, there's no known mechanism that will lead to the formation of structures. Leave alone the fact that if you have a cosmology with dark matter, you exactly reproduce many details of how structure forms. Without dark matter, structure wouldn't form at all. Okay. So again, the picture is these teeny initial density perturbations clump in their dark matter content while baryons float around. And eventually these big gravitational potential wells capture all the baryons. They then see these very deep potential wells, they fall in, start forming stars, start forming galaxies, and bigger structures form. Okay. So again, the universe is too young for structures to form without the seed of dark matter density perturbations. So you can go further. And in this simulation, which was run by my colleague Joel Primack and collaborators at the University of New Mexico, you can create on your computer, on your supercomputer, a simulation of the universe that you populate with particles that behave gravitationally like dark matter, and you just let it go. You just let it evolve in time. And what you do is you directly observe the formation of these clumps of dark matter. Okay, so what we're looking at here is how the universe would look like if dark matter were not dark. And we could actually see where the dark matter is. In fact, what we do see are things like this when they're populated with galaxies. So galaxies form because the dark matter has these high density contrast regions where baryons infall and stars start forming. In fact, our galaxy is more similar to one of these little clumps. This is more akin to large clusters of thousands of galaxies. But the general structure is one where the cosmos is filled in sort of a self-similar way. So clumps that are increasingly smaller in size. In fact, many such clumps don't host any galaxies at all. If the clumps are too small, they cannot attract enough baryons to star-star formation. So we think that, in fact, the universe is filled up with these smaller clumps that are yet to be detected. So you can say, okay, what do you make of this? Well, what you make are pictures where you take those simulations and you put in galaxies according to how big dark matter halos are, okay, with very well-defined prescriptions, and you compare observations and simulations. Where the observations are nothing but big pictures of large swaths of the sky. And you count things like 2 or 3 point correlation functions and density of structure as a function of scale, and blah, blah, blah. And you make a lot of predictions, and you compare, again, the right and the left. And they look amazingly similar in a very quantitatively testable way. But there's more. Dark matter is also essential to the way in which we observe the late time dynamics of cosmic structures to evolve. So for example, here in this little picture that I'm going to, I can let play, is a simulation of dark matter plus baryons, and a simulation that shows how the merger of two disk galaxies happens in n-body simulation, so in these computer-generated universes, versus real pictures of galaxies. So again, that was a simulation, that's a real picture, and simulation goes on, and it gets to a different snapshot, and then you compare, you rotate, because of course you don't get to choose where you look galaxies from, but you can rotate a cosmological simulation. You compare with pictures of the actual universe. And again, you can turn this beautiful picture into quantitative predictions. Do your simulations reproduce the pattern of galaxy mergers that is actually observed? And can you do that without dark matter halos encompassing these disky galaxies? Well, the answer is no. You need dark matter to reproduce the fine details of these merger processes. Now, that's all good, even if a little bit weird, but there's more. So, about 20 years ago, people realized that there's more to the universe than dark matter. And this was awarded a Nobel Prize back in 2011. And this has to do with what happens to the expansion of the universe. So if the universe were filled only with matter, you have this big explosion. You would have this big explosion, but the universe would be filled with matter, and so at some point you run out of steam and matter starts to recollapse gravitationally, okay, under its own weight. However, the universe doesn't look that way. The expansion of the universe is not slowing down. In fact, it's accelerating. So the rate at which the universe is expanding is measured to be growing with time. Okay, the rate at which the universe expands. So the acceleration itself, instead of slowing down as it should, if the universe were filled with matter, contains something that we don't know of, that makes the acceleration of the universe a positive quantity. So that makes the expansion of the universe increasingly fast with time. So you can imagine that you can measure, as a function of time, the scale of the universe, so the size of the universe. At the moment we are right here. And you know, if there's nothing that pumps the acceleration of the universe up, we're going to end up here. If there's a lot of this weird stuff that pushes the expansion of the universe to be accelerated, we're going to be up there. And if you're kind of in between, we are right there. So what scientists figured with the observation of essentially where these curves are, for where we can observe them, is that we are on the red line. So as far as we can tell today, we're going to have this constant expansion driven by a mysterious substance that, for lack of good names, we call dark energy. Yes?
What is the big crunch?
So the big crunch would be a recollapse of the universe under its own gravitational effects. So you've got a universe field of matter, and you know, as you run out of steam from the initial Big Bang, you recollapse under the weight of the stuff inside the universe itself. And so given certain energy content of the universe, you can predict whether or not you recollapse into a singularity. And that's not going to be the case, data say. Okay. So to sort of visualize what I'm conveying of this standard cosmological model, you've got two competing effects in how structures form in the universe. First, you have the dark matter that weighs things down, that makes galaxies form, that makes things to collapse and merge together. And on the other hand, you've got dark energy. So dark energy played essentially no role in the very early universe. We know that from direct measurement. But it's becoming a bigger and bigger deal as the universe ages. So later and later times, in fact, starting at about 5 billion years, the dark energy was the dominant energy component in the universe. So as my friend Rocky Kolb of the University of Chicago likes to put it, don't let the bright lights fool you, the dark side controls the universe. Dark matter holds it together, dark energy determines its destiny. Another friend of mine, who's now at Caltech, Sean Carroll, calls this a preposterous universe. I'm going to explain to you how we measure how much dark matter and how much dark energy there is in the universe. But we know pretty precisely that dark energy makes up about 70% today of the energy density of the universe. And dark matter makes up about 25%. So the rest of the stuff is really minor details. In fact, it's mostly just free hydrogen and helium and heavy elements that our friends in the chemistry department make a big deal out of are actually just 0.03% of the universe. So let me tell you a little bit about dark energy. So dark energy clearly is a big open problem. You know, 70% of the universe is in that form, but we know of a very, very trivial solution to the dark energy problem. That's called the cosmological constant. I'm not going to belabor on what these are, but these are Einstein's equations of general relativity in a very compact form. It looks like one equation. It's actually 16 equations. Mu and nu can be 0, 1, 2, or 3. And what G mu nu is, essentially, it's called the metric tensor, is the way in which the geometry of the universe looks like, okay, at a given point in time and space. So you've got these 16 nonlinear second-order differential equations. The right-hand side is a so-called tensor, T mu nu, which is called the matter-energy tensor, and it's got a component that truly has to do with what the universe contains. So, you know, matter, radiation, anything else. But there's also this piece, which, notice, comes with a minus sign, which is called the vacuum energy. So that's a piece that Einstein was very well aware of. In fact, Einstein himself postulated this piece because when he formulated general relativity, folks didn't know about the expansion of the universe. And Einstein actually postulated this term to curate the fact that in his theory the universe would expand, unless there was such term. Of course, the universe does expand, and so Einstein went back to saying, well, this term must be 0. But he was wrong again. He was wrong because the universe expands at an accelerated rate, and that has to do with the fact that this term here actually does exist. Very, very small, and it has kind of the wrong sign if you think about it as a fluid. You can think of fluids as simple objects where you relate the pressure to the density. Okay? So for example, matter is a pressure-less fluid. Radiation is a fluid with a very large radiation pressure. Well, the vacuum energy is a negative pressure fluid. So it's a fluid that drives sort of the accelerated expansion of the universe because it acts as anti-gravity. Okay? Its presence repels matter away. Okay, so weird stuff, but stuff that theoretically was long known to possibly exist. And here's a rare picture of Einstein working on dark energy back in the day. So dark energy, in my opinion, is definitely worth thinking about, but we do know of a very, very well-justified and compelling candidate, the cosmological constant. Now, my theory colleagues work very hard at thinking about why that constant has that value. But to me, that line of investigation is sort of sterile. You can ask the same question about the mass of the electron. Why is the mass of the electron 511 keV? I don't know. I don't have a good answer. It's a constant. It would be great to have a theory that explained in detail the value of the mass of the electron, the muon, and blah, 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 all of the elementary particles, as well as the electromagnetic constant and so on. But I think the fact that there is a natural theoretical candidate makes this type of inquiry not as profound as other questions are. So let me get to dark matter. So dark matter is something that we can measure very well for essentially the following reason. Because we can do subtractions very well. So we can measure the total matter content of the universe, which is on this right axis, quite accurately from a variety of different pieces of information. This is the so-called baryonic acoustic oscillations. I'm not going to explain what these are, but as you can see, they're very sensitive to how much matter there is in the universe. This is the cosmic microwave background. These are supernovae. On the vertical axis, you've got how much dark energy is there. Okay, so from this plane and the fact that these three pieces of information intersect only here, allow us to say that the total matter density of the universe has a very narrow range. Now, we also know the baryonic matter density quite well. In fact, I've already told you how to measure that from light elements and the cosmic microwave background. So by taking the 30% or so total matter density in terms of the total energy density of the universe, minus the 4% of baryonic matter density, gives you a leftover amount of 26%. That is how we measure the abundance of dark matter in the universe. So when it comes to the matter density itself, the dark matter is really the huge submerged part of the iceberg, right? It's 85% or so of the global matter content of the universe. What do I call matter? We're stuff that interacts gravitationally. Okay, the dark energy obeys the laws of general relativity, but it doesn't behave as matter. Okay, it's not a pressureless fluid. So why is it so important to think about dark matter? Well, I think it's so important for the following simple reason. That when you look at the known particles of the standard model of particle physics, we've got no candidates for the dark matter. So let me walk you through why that is. So certainly dark matter must be stable. So things like the Higgs boson or gauge bosons of electroweak interactions don't work. These guys decay on a millionth of a second timescales. Galaxies live for 10 to the 17 seconds. So that's not going to work. You've got quarks here and the gluon. All of these guys interact strongly. That cannot be the dark matter. Otherwise, we would have seen it. Dark matter would have interacted with nuclei, and we would have detected it. So that doesn't work. Also, dark matter is dark, cannot have an electric charge, so it cannot be photons, clearly, but it also cannot be electrons. These guys are unstable. Dark matter is not made of electrons for sure. So you've got this last little piece of code in the standard model of particle physics called neutrinos. Turns out that neutrinos also cannot be the dark matter, and the reason is slightly more subtle. So neutrinos are neutral. We know they are massive from direct experiments. But the problem is that neutrinos are very, very light. They're so light that they move relativistically in the universe as structures form. And so that trick that I was telling you about of collapsing structures to form the seeds for the formation of galaxies doesn't work. Okay, because neutrinos, when structures form, are relativistic. They move essentially at the speed of light. And so they just don't collapse gravitationally, not because they have electromagnetic pressure, but because they have very large speed. That's why the standard cosmological model is often called the cold dark matter cosmology. You want dark matter particles to be cold, to be moving slowly in such a way that collapse of early density perturbations can happen. So neutrinos, sadly, also cannot be the dark matter. So for a particle physicist like me, this is extremely interesting because probably it's the cleanest and most compelling evidence we have so far for new physics beyond the standard model. We need a new ingredient. We need something new besides the particle content of the standard model. So that's why, literally hundreds of thousands of papers have been written and hundreds of thousands of millions have been spent searching for dark matter. So let me summarize what I've talked about so far. So modern cosmology, I claimed, is a scientific theory. It's a scientific theory because it makes quantitative, testable predictions that are mathematically consistent and that are economical. Okay, so modern cosmology has two key ingredients in addition to what we know and love in the universe. These two ingredients are dark matter, which seeds the formation of structure, which is responsible for the formation of large clumps of matter where the stars form in the early universe, and dark energy, which is responsible for the accelerated expansion of the universe. In addition, of course, to all of the stuff we know, such as particles and general relativity, and the way in which these interact in the early universe. So dark energy is the big guy in the energy budget of the universe today, but it has a very natural, very compelling explanation that to me is completely fine. And observation is completely fine too, the cosmological constant. Okay, so from a field theoretic standpoint, it's absolutely trivial to explain the existence of the cosmological constant. It's absolutely non-trivial to explain its value. Okay, to explain why the cosmological constant has the value it has. Some people say, well, if it didn't have the value it has, the universe would not form, there wouldn't be observers, and therefore it's completely meaningless, and we got to take those values of the cosmological constant out of the picture. That's a so-called landscape theory that also kind of meshes with the notion of anthropic principle. Okay, you need observers, and observers only can exist if the cosmological constant has that value. Now, is that a good explanation? I don't think so. I don't think that is a compelling explanation to the value it has. But again, it's just as interesting a question as asking what the mass of the electron is or what the charge of the electron is. Much more interesting to me is the question of what is the dark matter. And that's what I'm going to tell you guys about. So in principle, dark matter can be completely dark. It can easily not have any meaningful interaction with us whatsoever. And the universe would be just fine. But we tend to be optimists. And if you are an optimist, like me, you think that maybe at some level, to some degree, the dark matter does have some interactions with our world, with the visible world. We don't know what that interaction is, but in particle physics language, you can think of a dark matter model as being defined by what the weight of the dark matter as a particle is, by its mass, number one, and number two, by how strongly this particle here, chi, interacts with particles in the visible sector, in the standard model, such as quarks or electrons, photons, and so on. So you've got, on the one hand, the mass of the particle, on the other hand, how strongly that particle interacts with us. Okay, so that's your parameter space. Now, theorists like me are very creative. So if you look at this plane, where again you've got the mass and the interaction strength of the dark matter particle with visible matter, just look at these numbers. Okay, it goes from 10 to the minus 33, a GeV is roughly the mass of a proton. So we're talking about 10 to the minus 33, the mass of the proton, all the way up to 10 to the 19 times the mass of the proton. So basically we have no idea what the mass of the dark matter particle is. We have no idea. Okay. And the interaction cross-section is even worse. It goes from 10 to the minus 39 in these units, picobarn, to 10 to the 24. Okay, roughly picobarn is the strength of proton on a proton collision. So again, we have no idea. All we can do is come up with models which are more or less fancy, more or less justifiable on the basis of theoretical arguments, or maybe on the basis of aesthetics, and populate this parameter space. So a lot of people think, including me, that there's a region of parameter space that is particularly interesting. And the reason is the following. So there's one thing we know very well about the dark matter, its abundance. So if you live in this purple region here, well, the strength of interaction and the mass are such that the abundance of the dark matter from the early universe comes out to be just right. Okay, so in just the same way as light elements have an abundance that you can calculate as a function of one parameter, here you can think of exactly the same thing happening. So from the thermal history of the early universe, if you have a weakly interacting massive particle, a particle with a mass at a weak interaction scale, and weak interactions, it turns out that its abundance is exactly the abundance of the dark matter that we measure in the universe. So that's an interesting argument. It's one possibility. Okay, and people have gone off and assumed that then this white blob is weak interactions. Okay, the interactions that, for example, mediate the decay of the neutron, things we know very well from many decades ago. And so if that's the case, then you have some room to play in looking for the dark matter as a particle. And that's the business that I've been in for many years now. So for example, you can take two particles of dark matter, and these particles can self-annihilate, producing things you can measure, such as photons, or antimatter, or neutrinos, things you can actually go out and measure. So that's called indirect detection, because you indirectly detect the debris of these annihilation processes of the dark matter. Then there's this other line of business that I've also been very involved in, called direct detection, where you want to measure is the scattering of the dark matter off of ordinary matter. You see, you have a dark matter particle. Here, imagine you have a proton, and the dark matter kicks the proton and gives the proton a little bit of energy, momentum. Okay? And so I understand next week you're going to have a speaker who's going to tell you everything about how very smart experimentalists are trying to measure these teensy-weensy energy depositions that the dark matter is predicted to impart to ordinary matter as it shoots through our position in the galaxy. Then finally, you have another direction at which to look at this diagram, which is, well, maybe I can take two protons, smash them together, and produce the dark matter in the lab. Okay? So that's actually completely uninteresting, because if you do produce dark matter in the lab, you're not going to see it. It's so hard to see. But there is some silver lining. The silver lining is the following, that you can radiate stuff from the initial state, such as photons or jets. And so there's a lot of very smart experimentalists at CERN with the Large Hadron Collider who look for stuff they can't see. They call it missing energy or missing transverse energy and momentum, plus monojet or monophotons. So events that essentially have nothing, plus one single photon, very high energy, or one single jet or stray of particles. Okay, so you've got different ways, if the dark matter is in that particular corner of parameter space, to look for the dark matter. So let me give you a little bit of an overview of where we stand in searching for this type of dark matter. So here's the CERN LHC, it's this ginormous experiment I'm sure you've heard of in Geneva, Switzerland. CMS and ATLAS, but also indirectly LHCb, are actively looking for this missing energy plus stuff events. Nothing has been found so far, but the parameter space is still pretty open and unconstrained. So let me tell you just in one slide, direct detection. So direct detection, again, you have dark matter shooting through at a pretty high rate our position in the galaxy. Occasionally, you can kick either nuclei or electrons of ordinary matter, and maybe you have such a good experiment that you can distinguish that tiny energy deposition, we're talking about kilo-electron volts down to milli-electron volts energies, from anything else that could produce such things, for example, free neutrons, naturally radioactive, and other things. So if you're very smart, you control your background well, you can set limits or discover dark matter. And in fact, this is an old plot that shows where theories like me think dark matter could exist in this parameter space. Again, the same as before, the mass versus the interaction strength. There's some experiments actually in Italy that has claimed for many years a positive signal. So they claim to have detected dark matter. The problem is that they're being very mysterious with their experiments. So they don't let, for example, other experiments use the same crystals that they use, the same detectors as they use. So that, is very exciting because science works by being reproducible. Okay? You want experiments that, if I don't believe what you find, I'm going to set up my experiment and check your results. So that doesn't seem to be possible with this Italian experiment. And also, these are the exclusion limits from a bunch of other experiments that are therefore ruling out the results of these Italian experiments. So the jury is still out. They might have something, but they're being really unfair to the scientific community by being secretive with their experiment. Of course, their thinking is, well, we're sitting on a Nobel Prize thing here, and so we're not going to let anybody else work on it. But that's not how science works, or should work. So anyways, I've been in this business of indirect detection for a long time. And the reason is that there's a lot of things that can come out from this self-destruction or annihilation of dark matter particles. So one of the things is antimatter. Antimatter exists in the cosmic radiation. It's measured. It's actually pretty abundant, maybe 1 part in 10 to the 4. But it's rare enough that if dark matter, by annihilating, produces any antimatter, we should be able to measure it. We should be able to see those little bumps on top of normal cosmic ray processes. Gamma rays, the Fermi telescope, has been used extensively to search for dark matter. But also, Fermi has been used to search for positrons and electrons from dark matter. And I've been very involved in that. Dark matter can also produce other frequency photons. I'm lucky enough that my wife is an X-ray astronomer, and so we've collaborated a lot looking for dark matter with X-ray telescopes. That's been a lot of fun. Radio telescopes also can be used to look for axions or even for WIMPs, for these weakly interacting massive particles. And then you've got neutrino telescopes, huge telescopes, kilometer-sized detectors that exist under the sea or even under the South Pole. That's a whole different colloquium. So all of these messengers are out there and they're ready to be used by people working on searching for dark matter. So the question to a particle physicist like me is, can we use these messengers in ways that inform, particle physics, in ways that are clear and crisp experimentally enough to learn about new physics from a particle standpoint. And that's been a fun area to be in. So I've worked a lot, for example, on this particular signal, which is an excess of high-energy positrons in the cosmic radiation that you see up here. The prediction for cosmic rays are down here. So you get a signal. About 10 years ago, I was one of those claiming that that's exactly what you expect from pulsars. So you've got astrophysical objects that could fake the signal very well. This has been in the news again recently. There's been new detections that inform that signal. Hundreds of papers have been written on an axis of gamma rays from the center of the galaxy, which looks precisely as what you would expect from dark matter annihilation. So there's been a lot of excitement. My group has worked a lot on understanding what, ordinary processes from cosmic rays or even from the supermassive black hole at the center of the galaxy could obfuscate this signal and could fake this signal. And we think that that's not dark matter, it's probably astrophysics. But again, it's been a very interesting possible signal of dark matter. Recently, again, in X-rays, there's been, well, if you want to call this a bump, I don't know, but people claim that there's a bump here at 3.5 keV. We've looked at that very closely. People were certainly certain to have discovered dark matter in the form of stellar neutrinos of 7 keV mass, and we think it's just potassium atoms being excited. So, given the fact that the mascot of Santa Cruz is the banana slug, and given the fact that we think it's potassium, we wrote a paper called "Dark Matter Searches Going Bananas," which actually made fun of work done at Harvard. So, we send the Harvard folks, no, not made fun, but referred to work done at Harvard. So we send them the paper before putting it on the archive. They get back to us being like, you don't dare do that. Of course we did it. But it was fun, the social aspects of science. Anyways, we don't think that's dark matter. It's probably bananas. So we've got excesses of anti-helium-3 that also have caught my attention. But I'm running out of time. And so more recently, we've actually kind of switched away from this WIMP story. And what LIGO detected, these black holes mergers, we think could actually have to do with dark matter. In fact, we've calculated what the maximal amount of black hole dark matter could be in the universe, given everything we know about black holes and everything we know about dark matter. And our conclusion is that yes, it is a possibility that primordial black holes, so black holes that don't come from the end cycle evolution of stars, but they're primordial, they're produced in a very early universe. Those black holes could be the dark matter. And they could be what we're seeing with LIGO, where we're seeing gravity wave mergers. So I don't have time to talk about the other mystery that we have, which is where ordinary matter comes from. And I think, the key problem here is that we've got a very small asymmetry. It's 1 in 10 to the 10. We don't know where this asymmetry comes from. There's a famous saying in mathematics that there are enough small numbers to meet the many demands made of them. But we'd like to understand this small number in terms of new dynamics. And again, I think, going back to this, the key aspect, there's many theories of baryogenesis at very high scales that are all untestable. The theory that I've been working on operates at very low scale, at a scale that is being tested with the Large Hadron Collider. And that's why I think it's an interesting theory to work on. It's called electroweak baryogenesis. And I'm going to leave you with this. Electroweak baryogenesis actually predicts gravity waves from a very early universe, from times that are a tenth of a billionth of a second. And for those gravity waves, unfortunately, they peak here in the millihertz frequencies where current detectors don't work, but as you might or might not know, the next generation gravity wave experiments are going to be sent in space. The Europeans are on top of this. NASA was like, well, first detect gravity waves and then we're going to be on board. So NASA is on board now, eventually. And so I was collaborating with ESA on this. This is an amazing, amazing detector. So look at the scale. This is Sun, Mercury, Venus, Earth, and this is where the detectors are going to be way out in space. And these are going to be the interferometry legs of the detectors, shining lasers against each other with no seismic noise at all. So I'm going to leave you with this. Cosmic puzzle is far from being solved, but I think, especially for the young folks in the room, and for the old folks, there are exciting opportunities to write new chapters in the book of science. And I'm going to leave you with this.
Well, thank you very much for that presentation. It was a wonderful talk to have. I know we're approaching 5 o'clock and many of our extra credit students have other commitments at that time. So at this point, those students who are here for extra credit are welcome to depart. Please do so as quickly and quietly as you can, and we will take questions from the rest of the audience at that point. Our speaker will be staying for dinner with us tonight, so if you're interested in joining us for that, please come and see me at the end. Otherwise, in just 30 seconds, we'll start up questions from the audience.
Thank you.
Do you have the stamp? Yes, I do.
Great talk. Oh, thanks.
Thank you so much.
Thank you so much. Yeah, you're welcome. Cheers.
Thank you.
Next page. Actually, can we have you do that over here?
Yeah.
Let's do that.
Thank you. Yeah.
Scott, first question.
Yeah, primordial black holes. Is there something important about the timing of their formation and not to contribute, in baryogenesis in these very remarkable, the deuterium, the lithium requirements, right? I mean, if they're ordinary matter that's going to become a black hole, it's going to change that. So what are the thoughts about primordial black holes?
Yeah, so first of all, since, as you say, Big Bang nucleosynthesis provides a very crisp measurement of the amount of baryons in the universe, you definitely cannot have any substantial fraction of the dark matter be in the form of astrophysical black holes. So these objects form typically, standard formation scenarios at the end of inflation, where you have some period where, for whatever reason, probably has to do with how inflation ends. So during reheating, you have some amount of high density fluctuations that are so large that they literally collapse in black holes at very, very early times. So we're talking about temperatures on the order of maybe 10 to the 15 GeV or so. So these guys, depending on their mass, they can evaporate. So they evaporate always, in any case, through Hawking radiation. But they can evaporate early enough to disrupt Big Bang nucleosynthesis. So once again, if you have light enough black holes, their lifetime is inversely related to their mass. So the lighter they are, the quicker they evaporate, the more energy they inject. So if that's the case, so for example, for black holes of 10 to the 17 grams or so, or lighter, these guys evaporate during the history of the universe, and you perturb all sorts of things. So they're very strongly constrained. But black holes that are primordial and they have masses in the tens of solar mass range definitely, do not create any problems from the standpoint of evaporation. They evaporate very little. They don't perturb anything, but they're so massive that they do create problems in the stability of structures, such as, for example, dwarf galaxies or Doppler clusters. So there are some constraints on very massive primordial black holes from that. So there's a variety of constraints, and as you know very well, there's constraints for microlensing on these objects as well across a wide variety of masses. But what we found was that depending on the mass distribution of black holes, you can have the entirety of the dark matter be of primordial black hole origin.
You had your diagram of a parameter space and potential different explanations of dark matter. You said the WIMP box sits, I think convenient was the word you used, in the middle. I didn't catch though if there was any sort of meaningful indications that it should be there, or just that it fits nicely into what we have so far.
Yeah, so that's a great question. So from a theoretical standpoint, WIMPs have been sold and marketed based upon the fact that the standard model particle physics does require, to some extent, new physics at the electroweak scale for a variety of reasons. One of them is the so-called hierarchy problem. Another reason is gauge coupling unification. And so having new physics at the electroweak scale always seemed like something very compelling and very plausible. The LHC has not found any evidence of strongly interacting particles at electroweak scale. It really doesn't have much to say about WIMPs at the electroweak scale, other than the searches I've mentioned. In addition to this, what WIMPs are from the standpoint of cosmology are perfect thermal relics. So in just the same way as we think that deuterium is mostly a thermal relic, so if you have a particle with a mass of about 100 times the mass of the proton and weak interactions, then its density today is pretty much right. It's pretty much the dark matter abundance. Exactly the same way as if you have a baryon density that is what we observe, you produce the right amount of deuterium. So that is a sort of independent, theoretically independent motivation for WIMPs. If it comes to primordial black holes, why should there be that many primordial black holes? There's no good reason. You can cook up an inflation model that produces them in the right amount, but there's no compelling reason for there to be that many primordial black holes. Yes.
It's possible you covered this in your lecture, and it's also very possible it went right over my head. So allow me a fundamental question. If dark energy is that great a force that it's accelerating the universe constantly, how did the matter that was remaining manage to coalesce into all these galaxies and other phenomena in the universe?
Yeah, so that's really a good question, and the answer is that if you look at the energy density of dark energy, I don't know if there's anything I can write here, but so the energy density of the dark energy was, well, if it is a cosmological constant, was very, very, very low at the time when structures formed. So a way to think about it, I really wish I could draw, but if you think about when photons and electrons decouple, CMB decoupling, well, at that point in time, matter was 1 billion times denser than dark energy, 1 billion times. Okay, and radiation was pretty much the same as matter. Now, today, the dark energy, so the slope is kind of like this. So as you go backward into the universe, this is matter. This is a cosmological constant, it's a constant. So it's only at very, very late times that the universe and structures in the universe has started to feel the gravitational effects of dark energy. But your question goes back to, so maybe this is not a constant. So maybe this is not a constant. So maybe it's something dynamical. In fact, I've worked on scenarios where the dark energy is not a constant, but rather it's a dynamical field that has interactions with other stuff in the universe. And so in that case, you can put very meaningful constraints on preventing that the dark energy disrupts structure. But the way you do it is essentially, well, when structure formed, the dark energy was not behaving as dark energy. Okay, so you do know that that you have to have subdominant dark energy when structure forms, for precisely the reasons that you were saying. Yeah. Yes.
I thought there was still this 10 to the 120th power problem about the cosmological constant being constant.
Oh, good, good. So, so believe it or not, there is an undergraduate student from somewhere in Northern California who keeps writing me that he solved the cosmological constant problem because he figured that if you have a scalar field and you calculate the vacuum energy of a scalar field, then you can set what technically is known as the cutoff scale, where so again I don't have anything to write, but if I did, I would write an expression where you have a quantity with the dimensions of momentum or energy that would go as the fourth power. So you have essentially some physics scale. You mentioned these 120 orders of magnitude. That refers to the fact that if you have a vacuum energy associated with a field, and so this vacuum energy depends essentially on the fourth power of the highest possible momentum that the field can have. So if this highest possible momentum is at the scale of quantum gravity, then you have this 120 orders of magnitude match. You should have a huge cosmological constant. Now, particle physicists are very brave individuals, never scared by infinities. We know how to take care of infinities. And the way you take care of an infinity is you write infinity minus infinity equals whatever you want. Okay? Just true, it's mathematically true statement. And so that's how we do renormalization. So that's what you do. So the point is how fine you have to cancel infinity against infinity. Okay, and so the 120 orders of magnitude just depends on the fact that you think your cancellation is not good enough up until when quantum gravity sets in. So certainly that 120 orders of magnitude is cancelled away, okay, by renormalization. But the problem is that there is this leftover of infinity minus infinity. And the question is why that is such a small quantity. Okay, so technically there's no problem in the 120 orders of magnitude, but a big fine tuning. So some people are very psychologically disturbed by fine tuning. I just am not. So what can I tell you? I think it's more of a psychology kind of question than a physics question.
So it seems to me like this is really a gravitational mystery, the whole idea of dark matter. And without a quantum theory of gravity, or do you need a quantum theory of gravity, you think, to solve this mystery, to incorporate it into the standard model?
Thanks. So I was actually fearing your question for a moment because nobody has yet brought up modified gravity, which is yet a whole other. So I can give you a colloquium on that. I'm not going to do it, but so to answer your question, no, quantum gravity has probably nothing to do with this. These are very, very low energy phenomena. So for example, dark energy is something that you can think of as having an energy scale. Again, it's not a Planck scale. It's 10 to the minus 4 electron volts. And we know that quantum gravity starts to set in at 10 to the 19 giga electron volts. So those are many orders of magnitude. So it looks, you can think of this in terms of distances. You can convert energy scales, 1 over, and so that means that quantum gravity affects distance scales which are, maybe a billionth of a billionth times smaller than the size of an atom, while dark energy affects scales on scales the order of galaxy clusters. So it's just a different realm of. So there's probably nothing that once my smart colleagues figure out quantum gravity, that would have to say. In fact, it's kind of disturbing that even if you talk about black hole mergers, and you say, well, that's definitely, it must have something to do with, quantum gravity. In fact, it doesn't. But it doesn't even almost have to do with general relativity. So the treatment of black hole mergers is vastly Newtonian. Up until the very, very last moments, Newton gravity works just fine. And then, there are some GR effects that you have to build in because, black holes are intrinsically GR objects. But quantum gravity just, operates on scales that are vastly different from where cosmology operates. Now, this is not true of the very, very early stage of the universe. So if you go down to 10 to the minus 44 seconds, then for sure quantum gravity was relevant back then. But we think that those stages are completely untestable directly because there was this thing called inflation that made us lose memory of anything that happened before inflation. So I don't want to sound too pessimistic, but I think quantum gravity and cosmology have a long ways before they talk to each other.
Well, now I fear fine-tuning and quantum gravity. As we have to turn over the room to the next class in just a few minutes, we're going to wrap up at that point. If you have any further questions for our speaker, come catch them at the end. Otherwise, let's thank him again.